Bismillahirrahmanirrahim. Our today's lecture is about binary arithmetics for unsigned numbers. Binary arithmetic for unsigned number. The agenda of today's lecture include binary addition, binary subtraction, binary multiplication and binary division. Binary subtraction using 1's complement and 2's complement, decimal subtraction using 9's and 10's complement, hexadecimal addition and subtraction. Binary arithmetic. Binary arithmetic is essential in all digital computer and in many other types of digital systems. To understand digital system, one must know the basics of binary addition, subtraction, multiplication and division. Binary addition. The four basic rules of binary addition are 0 plus 0 equal to 0, sum 0 with carry 0. The second rule is 0 plus 1 is equal to 1, sum 1 with carry 0. When we add 2 bit, so the sum contains 2 bits. One is called the sum and the other is called the carry. 1 plus 0 is equal to 1. The sum is equal to 1 with carry 0, and 1 plus 1, the fourth rule, equal to 1 0. Keep in mind, in binary 1 plus 1 is always equal to 1 0. It is not equal to 2. Sum 0 with carry 1, the sum bit is 0. The two numbers in an addition are the addend and the adjoint. The result is called the sum. So addition of 2 bits results in 2 bits. One is called sum and the other is called carry. Example of binary addition. Let's take this example. We have these two binary numbers. One number is 0 1 1 and the other number is 0 0 1. This is addend and this is adjoint. So to add this number, let's start from the first column. From the LSB, least significant bits. So 1 plus 1 is equal to 1 0 according to rule number 4. 1 plus 1 is equal to 1 0. So 0 is the sum bit. So we write the sum bit under the column and carry the carry bit to the next column. So this is the carry generated from this column. So here 1 is a data bit and this one is a carry bit. So when we add these two bits, 1 1, again according to rule 4, it will result in 2 bits, 1 0. So 0 is sum, so we place a sum under this column and we carry 1 to the next column. So this is the carry. 0 plus 0 is equal to 0 according to rule 1, and when we add 1 to 0, so we get 1. 1 plus 0 is equal to 1. So this is the sum of these two binary 3-bit binary numbers 1 0 0. When there is a carry of 1, we have a situation in which 3 bits are being added, a bit in each of the two numbers and a carry bit. This situation is illustrated as follows. This is a carry bit and these are the data bits. So 1 plus 0 equal to 0 1. 1 is the sum bit and 0 is the carry bit in this situation. This is a carry again. So 1 plus 1 plus 0 equals to 1 0. The sum here is 0 and the carry is 1. 1 plus 0 plus 1 is equal to 1 0. So when we add 2 ones, so we get 1 0. When we add 3 bits, we add 1 1. The sum is 1 with carry 1. So this is the carry bit and this is the sum bit. When we add 3 ones in binary, we get 1 1. This is another example. These are two 8-bit numbers, addend and adjoint. This is addend number, this is adjoint number. So let's add them. So this is 1 plus 1 is equal to 1 0. So 1 is 0 is written here under the column, under this column, and 1 is carried to the next column. So 1 plus 1, this 1 in red represent the carry generated from the preceding column. So 1 plus 1 is equal to, again, 1 0, and we place a 0. 0 is sum, and 1 is carried, and 1 is carried to the next column. So 1 plus 0 plus 0, this is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 1 0. So 0 is written here, and 1 is carried to this column, and these are 3 1s. So when we add 3 1s, as we have discussed in the previous slide, so 1 plus 1 plus 1 equal to 1 1. So 1 is sum, and the other one is carry. So 1 is the sum is written over here, and the carry is moved to the next column. So 1 plus 0 equal to 1, and 1 plus 0 is equal to 1. So this is the sum of these two binary numbers. This is another example. This is another similar example. So when we add these two ones, so we get 1 0. 1 is carried. When we add these 3 1s, so we get 1 1, and 1 is carried to this column. 1 plus 1 is 1 0. So 1 is carried to this column. 1 plus 1 plus 0 again equal to 1 0, and 1 is carried to this column. 1 plus 1 again is 1 0, and 1 is carried to this column. So when we add 3 1s, we get 1 1. So 1 is written over here, and the carry 1 is moved to the next column. So 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0 1. So this is the sum of these two binary numbers. Binary subtraction. The 4 basic rules for subtracting bits are as follows. 0 minus 0 generates 0. 1 minus 1 generates 0 equal to 0. 1 minus 0 is equal to 1. So these 3 rules are very simple. This is simple subtraction. 0 minus 1, when the minuend is 0 and the subtrahend is 1, so 0 minus 1. For this situation, we need a borrow from the next significant position. So when we bring a borrow to this 0, so this becomes 1 0. So 1 0 minus 1 equal to 1. So this is 0 minus 1 situation with a borrow of 1 from the next column. A borrow is required in binary only when you try to subtract a 1 from a 0. In this case, when a 1 is borrowed from the next column to the left, a 1 0 is created in the column being subtracted, and the last of the 4 basic rules just listed must be applied. This is the 4th rule, so this rule must be applied. 1 0 minus 1 is 1, and this is the situation. Example, perform the binary subtraction of 1 0 0 1 1 0 minus 1 0 1 1. So this is the minuend, and this is the subtrahend. So 1 minus 1 is 0. 0 minus 1. So this is here we will apply the 4th rule. We will bring a borrow from this one over here, so it will become 1 0, and we will lift 0 or here. So 1 0 minus 1 is equal to 1. This is the 4th rule of subtraction. 0 minus 0 is 0, and 1 minus 1 is 0. So this is what the difference of these two numbers in binary is 0 0 1 0. Binary subtraction of unsigned numbers using complement. Subtraction is a special case of addition. Basically, the subtraction operation changes the sign of the subtrahend and adds it to the minuend. The sign of the subtrahend can be changed by taking its complement. We have discussed the taking complements in binary number system in the complements lecture. So complements changes when we take complement of a binary number, so we are going to change its sign. So this is the procedure they used by digital systems to perform subtractions. So in binary number system we have ones complement and we have twos complement, so we can perform subtraction using ones complement and we can perform binary subtraction using twos complement. The twos complement subtraction, twos complement method is more efficient. Ones complement subtraction. So the procedure to perform ones complement subtraction, so add ones complement of the subtrahend, means take the complement ones complement of the subtrahend and add the ones complement of subtrahend to the minuend. If there is an end carry, add 1 to the sum. If there is no end carry, take ones complement of the sum and place a negative sign in front. So in ones complement subtraction, let's perform this example. So we have two parts in this example, x minus y. So 1 0 0 1 1 0 1 0 1 0 0. So this is the subtrahend and this is the minuend in this example. X is the minuend and y is the subtrahend. In this example, y is the minuend and x is the subtrahend. This number is subtrahend. So in ones complement form, we have to take ones complement of this number, and in part B we have to take ones complement of this number and then add this ones complement of the subtrahends to the minuends. So solution x minus y. So subtrahend is y 1 0 0 0 1 1. So ones complement of the subtrahend, as you know how to take ones complement, so simple method is change all ones to 0 and all zeros to 1. So this is zeros, these two ones is replaced by these two zeros, and these 4 zeros are replaced by 4 ones, and this one is replaced by this 0. So this is ones complement of y, ones complement of subtrahend. This is minuend and this is ones complement of subtrahend. So we add ones complement of the subtrahend to the minuend. So this is the minuend, this is the subtrahend, and this is binary addition. So all binary addition rules will apply here. 0 plus 0 is equal to 0, 0 plus 0 is equal to 0, 1 plus 1 is equal to 1 plus 1 is equal to 1 0. So 1 is carried to the next column. So 1 plus 1 is equal to 1 0. So 1 is carried to this column. 1 plus 1 equal to 1 1. So 1 is written here and 1 is carried to this column. So 1 plus 1 is equal to 1 0. So 0 is written over here and 1 is carried to this column, and this is 0 and this 1. So this is the sum. So look, this is an 8-bit number, this is an 8-bit number, this is a 7-bit number, this is a 7-bit number, and the answer is 8-bit number. So the last bit, the answer, when we subtract two numbers, so the answer, the number of bits should be equal to the number of bits in minuend and subtrahend. So this one is called the end carry. This is the end carry. So in ones complement form, we add 1 to the ones complement. So difference is in ones complement form we add 1 to the sum bit. So in these bits in black, these are all sum bits, and this 1 in red, this is a carry. So we add carry to the sum bit. So to these bit we add plus 1. So 1 0 0 0 plus 1 is equal to 1, and all other bits will remain the same, 0 0 0. So this is the difference. So you have seen we have performed subtraction through addition. So complements allow you to perform subtraction through addition, and digital system uses this method to perform subtractions. This is this is the part B. So where the subtrahend is x, so we have to take ones complement of the subtrahend. This is ones complement of the subtrahend. We add this ones complement of subtrahend to the minuend. So this is addition. Again, this is addition process. So look, this is again a 7-bit number, so we have no end carry over here. So what we need to take ones complement of the sum of these bits. So this is ones complement of these bits, and put a negative sign in front of this number. So this is a negative number basically. Difference x minus y is equal to minus 0 0 1 0 0 1. So this situation occurs when minuend is less than the subtrahend. The second method is 2's complement subtraction, and this method is used by digital system. The procedure is as follows: add 2's complement of the subtrahend to the minuend. If there is an n carry, discard it. If there is no n carry, take 2's complement of the sum and place a negative sign in front. So example, subtract a, this is the a part, 1 0 0 0 1 1 from 1 0 1 0 1 0. So it is very important, you have to identify the subtrahend. So this number is the subtrahend in this. We have to subtract this number. So subtrahend is the number which is subtracted. So this is the subtracted. This number is the subtrahend. In this part B, this is the subtrahend. So to perform this subtraction, take 2's complement of the subtrahend. This is the 2's complement of the subtrahend, and you know how to take 2's complement of the subtrahend. Take 1's complement and add 1 to 1's complement, so you will get 2's complement. So this is 2's complement of the subtrahend. So we add 2's complement of the subtrahend to the minuend, so we get this sum. This is we apply all the rules of binary addition over here, so you will get this number as a sum. 0 plus 1 is equal to 1. So 1 0 0 0 1 0 0 1. So this one is the n carry. These are 7 bit, sum is 7 bit, and this is the last carry, n carry. So discard in 2's complement subtraction, we discard n carry. So if there is an n carry, so discard it. So the n carry, this one has been discarded. So m minus s, minuend minus subtrahend, is equal to 0 0 1 0 0 1. So this is the difference. This is the second part. So the takes 2's complement of subtrahend. So this is the subtrahend. No, so this is the 2's complement of subtrahend. So we add minuend. This is the minuend. Add 2's complement of the subtrahend to minuend. This is the sum. So look, there is no n carry. When there is no n carry, we take 2's complement of the sum and place a negative sign in front of this number of 2's complement. So m minus s is equal to basically minus 2's complement of sum. This is the sum. So this is the 2's complement of the sum. So m minus s is equal to minus 0 0 1 0 0 1. So this is 2's complement subtraction. Binary multiplication. The 4 basic rules for binary multiplications are as follows. 0, when 0 is multiplied by 0, this is equal to 0. 0 multiplied by 1 equal to 0. 1 multiplied by 0 is equal to 0. 1 multiplied by 1 is equal to 1. Multiplication is performed with binary numbers in the same manner as with decimal number. It involves forming partial product, shifting each successive partial product, lift one place, and then adding all the partial products. So let's elaborate this by an example. So this is the same manner as we apply in decimal number system for multiplication. So this is the multiplicand, and this is change it. This is multiplicand, and this is multiplier. This number is multiplier. So first bit is multiplier to the multiplicand. So we generate 1 1 1. This is the output of the multiplication, the product. This is the first partial product. We multiply 0, so shift it, multiply 0 0 0, multiply by 1 is 0, and 0 multiplied by 1 is 0, so all zeros. So we have shift this column one to the left, one position to the left. This second partial product, this is third partial product. So this is when we multiply this 1 with these 3 ones, 1 1 1. So now add these partial products. So apply the addition rules, binary addition rules here for addition. So product sum of partial product. So 1, this is 1 plus 0 is equal to 1. 1 plus 1 is equal to 1 0. So 1 is carried here. So 1 plus 1 is equal to 1 0, and 1 is carried here. So 1 plus 1 is equal to 1 0. So 0 is sum and 1 is carry. So this is the final product, 1 0 0 1 1. To avoid confusion in addition for larger numbers, add two numbers at a time. So example, perform the binary multiplication 1101 multiplied by 1011. So this is the multiplicand and this is the multiplier. So let's multiply these two numbers. So this is the first partial product, we multiply 1 to the multiplicand, and this is the second partial product, we multiply this one to this multiplicand. So first take the partial sum. This is the partial sum. We add these two partial products. So 1 0 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1 0, and 1 is carried over here, so 1 plus 1 is 1 0. This is the final carry. So this is the partial sum. So we add first partial product, second partial product, and we add this. So now multiply this number to the multiplicand, so we get this partial product, and this is the partial sum. So add this partial product to the partial sum, so we get the second partial sum. 1 1 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, and 1 plus 0 is equal to 1. Now this is the last bit of the multiplier, so multiply this to this number, so 1 0 1 1, and this is the fourth partial product. This is the second partial sum, so add partial sum to the partial product. So 1 1 1, so 0 1, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, and 1 is carried over here, so 1 plus 1 is equal to 0, and this is the final carry. So this is the final product. So when we add two numbers at a time, so it will confusion will be, there will be no confusion. So to adding 4 columns and to adding 5 columns, so it creates confusion in addition. So to avoid this confusion, so add partial products and partial sums. Binary division. Division in binary follows the same procedure as division in decimal. So let's perform these two divisions. So 110 divided by 11, this is the divisor, this is the dividend, this is the quotient. So this is the ordinary decimal, like decimal division. So 1 is multiplied with 1, and we get 1 1. So we subtract this number from these two ones, so we get 0 0, and this 0 is brought down. So then this is 0, so you can place a 0 over here. So this is like decimal number system division. This is just like decimal division. So 1 0 1 1. So this is another example. So 1 1 0. So this one is taken over here by subtraction. 0 and 1 0 multiplied by 1, again 1 0, and this is the remainder. These are other two examples. So we can divide binary numbers like we divide decimal numbers. Division using repeated subtraction. Division is basically repeated subtraction. The procedure to use repeated subtraction for division is as follows. Step 1, initialize the quotient to 0. So quotient is 0. Subtract the divisor from the dividend using 2's complement addition. We have seen in 2's complement subtraction transform into addition. So 2's complement addition to get the first partial remainder and add 1 to the quotient. If this partial remainder is positive, go to step 3. If the partial remainder is 0 or negative, the division is complete. Subtract the divisor from the partial remainder and add 1 to the quotient. If the result is positive, repeat for next partial remainder. If the result is 0 or negative, the division is complete. This is an example. So this is add bit binary, this is divide this by this, so this is the dividend, and this is the divisor. So this is the dividend, and add 2's complement of the desired. To subtract this number from the dividend, so we add complements of this number to the dividend. So the 2's complement of this number is 1 1 0 0 1 1 1. So when we add, so this is the first partial remainder, this is the first partial remainder. So when you apply this procedure, so add 1 to the quotient. So quotient was initialized to 0, now it becomes 0 plus 1 equal to 1. So quotient become 1. So if you add 2's complement, again subtract the divisor from the partial remainder. So this is the 2's complement. When we take 2's complement, then we have to add to perform subtraction. So this is 2's complement addition. So add these two numbers. 1 plus 1 is equal to 0. 1 plus 0, 1 is carried, so 1 plus 1 plus 1 is equal to 1 1. So apply addition rules over here. So this is the third partial remainder. So we get a partial remainder, so we add 1 to the quotient. 1 plus 1 is equal to 1 0. This is binary addition. 1 plus 1 is equal to 1 0. Add 2's complement, again add to, this is not 0 and not negative, so we have to continue. So again add 2's complement of the divisor, so we get this partial remainder. So we add 1 to the quotient. So the quotient previously was 1 0, now it become 1 1. This is a binary addition. So again this is a partial remainder, and we add 2's complement of the divisor. So this is the 2's complement of this divisor. So add. So look at the end, this is the remainder. The remainder is 0. So 0 0 0 0, all bits are 0. So this is our stopping criteria. Add we have performed this subtraction using 2's complement. So add 1 to the quotient. So previously quotient was 1 1, now 1 1 plus 1 is equal to 1 0 0. So this division produce this output. Look, this is 0 0 1. So this is the quotient. So this is an 8-bit number, this is an 8-bit number. To make the quotient an 8-bit number, we paid these 5 zeros to the left. Decimal subtraction of unsigned numbers using complements. So through complements we can perform a subtraction in other number system. So in decimal number system, as we have discussed in the lecture of complements, we have two nines complement and tens complement. So we have nines complement subtraction and tens complement subtraction. The procedure is similar to the ones complement subtraction and twos complement subtraction in binary. So add nines complement of the subtrahend to the minuend. If there is an end carry, add 1 to the sum. If there is no end carry, take nines complement of the sum and place a negative sign in front. Tens complement subtraction, add tens complement of the subtrahend to the minuend. If there is an end carry, discard it. In binary twos complement subtraction, we discard carry. So here also we discard carry. If there is no end carry, take tens complement of the sum and place negative sign in front. So this is how we perform nines and tens complement addition in decimal number system. Example. So let's elaborate this by example. Using tens complement, subtract 5250 minus 1321. So this is minuend, this is subtrahend. So tens complement of the subtrahend is this. So take nines complement of this, subtract 8 digit from 9 and add 1 to the nines complement. So we get this number 8679. Add tens complement of subtrahend. This case add to the minuend. So when we add these two numbers, we get an end carry. This is a 4-bit number, this is a 4-digit, this is a 4-digit number, this is a 4-digit number. So the difference should be in 4 digits. So this is the end carry. In tens complement subtraction, we discard the end carry. So this is the result. This is the difference. 3929. So m minus n, minuend minus subtrahend, equal to 3929 in decimal. This is another example. Use tens complement to perform the subtraction. So again, this is the minuend. So look, for subtraction it is necessary that both the numbers must have the same digits. So this is a 4-bit number, this is a 5-bit number, so you can pad a 0 to the left to make it a 5-digit number. So minuend is made a 5-digit number by padding this 0 to the left. So 72532, then tens complement of this number is 27468. So we add, so look, this is a 5-digit number, this is a 5-digit number, and this is a 5-digit number. So there is no end carry. So there is no end carry. So what we have to do to find m minus s? So take tens complement of the sum and place a negative sign in front. So minus tens complement of this sum 30718, and the tens complement of this number is 69282. Take nines complement of this by subtracting each digit from 9 and add 1 to the nines complement. So you will get tens complement. So this is tens complement subtraction. Using nines complement, so these are examples of nines complement. So in nines complement we add, if there is an end carry, we add 1 to the result. If there is no end carry, we take nines complement of the sum and place a negative sign in front. So this is the nines complement of the subtrahend. So when minuend is added to the nines complement of the subtrahend, we get this result. So these 4 digits are sum digits, and this 1 is the end carry. So when there is an end carry, so add this end carry or 1 to the sum, so to these digits. So this is 9293. So m minus is 3929. So this is the same question as we have performed in tens complement using this number. So again, m add nines complement of s, and this is the sum. So look, there is no end carry. So to find this subtraction, take nines complement of 30717, and this is, and place a negative sign in front. So this is the number. Hexadecimal addition. Addition can be done directly with hexadecimal number by remembering that the hexadecimal digits 0 through 9 are equivalent to decimal digits 0 through 9, and that hexadecimal digit a through f are equivalent to decimal numbers 10 through 15. To add 2 hexadecimal digits, add their corresponding decimal equivalent and convert them back to hexadecimal. To add 2 hexadecimal digits, add their corresponding decimal equivalent and convert them back to hexadecimal. These are example. So we have 2 hexadecimal. This is a 2-digit hexadecimal number. This is another 2-digit hexadecimal number. Addend and adjoint. So first we add this column and this. So b to add b with 4 in hexadecimal. So b in hexadecimal plus 4 in hexadecimal equal to, b is equal to 11 in decimal, and 4 is equal to 4 in decimal. So perform addition in decimal. So 11 plus 4 equal to 15, and we have to replace this 15 by its corresponding octal digit. So the 15 is equal to f. 15 is in decimal is equivalent to f. So this column produce f. Now this column we have 2 and 8. So 2 in 16 plus 8 in hexadecimal equal to 2 is equal to 2 in decimal, 8 is equal to 8 in decimal. So 2 plus 8 equal to 10, and 10, for 10 we have this character, decimal 10 is equivalent to a in hexadecimal. So this is what the sum of these 2 hexadecimal digits. Now this second example, we add this 2 hexadecimal number df and ac. So f plus c, f in 16 plus c in 16 equal to, f is equal to 15 in decimal, c in hexadecimal equal to 12 in decimal. So add 12 and 15, so we get 27 in decimal, and 27, so convert it back to decimal. We know how to convert decimal into hexadecimal. So this has been converted back to hexadecimal. So this is the sum digit and this is the carry digit. So we place the sum digit over here under this column, and we take this one carry to the next column. We move this one to the next column as carry. So the next column, this column contains 3 digits: 1 plus d plus a, 1 plus d plus a. So 1 in hexadecimal equal to 1 in decimal, d in hexadecimal equal to 13 in decimal, and a in hexadecimal equal to 10 in decimal. So we add these decimal numbers, we add their decimal equivalent. So to add d and a and 1, so add their decimal equivalent of 1, decimal equivalent of d, decimal equivalent of a. So we get 24. So we have to convert back this 24 and convert this decimal to hexadecimal again. So when we add 1 plus d plus a equals to 18 in hexadecimal. So this is 18b. So the result of this addition is 18b. Hexadecimal subtraction. So hexadecimal subtraction. So how to perform hexadecimal subtraction? So takes 2 complement of the subtrahend by subtracting each hexadecimal digit from f and add 1. When we subtract each hexadecimal digit from f, so this is 1's complement hexadecimal. So to get 2's complement, we add 1. So this is 1. Step 2, add the 2's complement hexadecimal to minuend, discard any final carry. So we can perform hexadecimal subtraction using 2's complement in hexadecimal. So subtract, this is an example. So subtract the following hexadecimal digit: add 4 minus 2a. So this is 2a is the subtrahend. So 2's complement is hexadecimal. So subtract 2a from ff, each digit from f. So subtract this a from f, subtract this 2 from f. So when we subtract, so it becomes d5. D is 13, 5 d5, and we add 1. So this is basically the 1's complement in hexadecimal, and when we add 1 to the 1's complement, so we get 2's complement. So this is the 2's complement in hexadecimal. d6 is the 2's complement in hexadecimal. So this is minuend. So add 2's complement of subtrahend, d6. So this is the subtrahend. When we add, so we got an end carry. So discard end carry. So we have to discard this end carry. So the difference is 5a in hexadecimal. Keep in mind, in hexadecimal, f minus f is 0, f minus e is 1, f minus d is 2, f minus c is 3, f minus b is 4, f minus a is 5, and so on. F minus 0 is f. So to find a 1's complement in hexadecimal, use the subtraction. You have to subtract each digit from f. So, and when we add 1 to the 1's complement in hexadecimal, we get 2's complement in hexadecimal. So this is the last example. This is the example of hexadecimal subtraction. So it's all for today. Thank you very much.